Hello there. I'm going to go ahead and add a couple of examples to the integration by parts that you might find helpful. In the first video on this, I showed you the basic concepts of integration by parts, but here I'm going to show you a couple of things that you might find new and interesting. The first thing I'm going to show you is how to do what's called the foldback rule with parts integration. So let me just show you how this works. It's fairly clever. It's a very clever concept. So let's say we wanted to find the result of the integral for e to the x cosine x dx. Okay, so let's go ahead and do parts differentiation with let's let u equal e to the x, and then let's let the rest of it, the cosine x dx, let's let that be the dv portion. Okay, so we know that we can take the derivative and get du is simply e to the x dx, and then we can integrate this side and get that v is sine x. And then we use the formula uv, which would be e to the x sine x, minus the integral v du. So the integral v du would be sine x times e to the x dx. So that would just give me an integral for sine x. Now, let's apply the parts definition again, but this time let's do it for this this e to the x sine x dx. So this time I'm going to let u equal e to the x, and then dv will be sine x dx. And then when you take the derivative e to the x, just like before, you get e to the x dx. And when you integrate dv, you actually get v is minus cosine of x. Okay, now let's put this in for right here. Let me show you, because this could get a little confusing. So remember, I had this right here as the result of my first parts differentiation. My first parts integration. Okay, now notice that I need to replace this. Okay, and I can actually replace this with the parts differentiation. I keep saying differentiation, the parts integration for e to the x sine x. So let me show you what I've done here. I just went ahead and copied down e to the x sine x. Okay, so I copied that down, and then just to make sure you can see everything properly, I went ahead and copied this down, this integral down. Now what I'm going to do though is I'm going to replace this integral with what I'm going to get from my parts integration. So let's take a look at what would happen. So again, I would have e to the x sine x, and then I would have minus right here, so I'm going to put a minus there, and I'm going to put the result of that second integral in these parentheses here. So now let's just talk about how we would integrate this using parts. Okay, so we would take this, to integrate this, we would do the uv, so that would be e to the x times minus cosine x. So that would give me minus e to the x cosine x. And then we would subtract, so we're subtracting here, the integral of v du. Well, v is minus cosine x, and du is e to the x dx. So if you multiply minus cosine x by e to the x dx, you actually get minus e to the x cosine x dx. Now, let's simplify this just a little bit. So if I distribute the negative here, I'll get this. First of all, I'll bring down e to the x sine x, and then distribute this negative right here, and that'll make this term a plus. So that term is a plus e to the x cosine x. And now this is where you have to watch closely. for the integral, I have a minus here, I have a minus here, and I have a minus here. So when you do a minus times a minus times a minus, you get minus. So I now have minus that integral. Okay, now, so if you're looking at this, you can see I still haven't found the solution because I still have an integral here. Okay, but here's where the clever part comes in. Take a look at the integral on the left, what I'm trying to find the solution to, and then take a look at this integral on the right. Notice that they're the same thing except for the fact that the sign has changed over here. So here's what I'm going to do. What I'm going to do is I'm simply going to add that integral. So I'm going to add this integral to both sides of this equation. Now when I add this to the right hand side, all it's going to do is just cancel this, right? And then when I add it to the left hand side, I have one of those integrals, and then I'm going to add another one of those same integrals to it. So guess what that would do? That would give me two of those integrals. So basically I kind of folded this back to the other side and it gave me two of them. Now, so I get two of these integrals is equal now to the terms that were left, e to the x sine x plus e to the x cosine x. And so now to solve for that integral, all I have to do is divide both sides by 2. So if I divide this side by 2, that will just cancel the 2, right? And then I would just divide these by 2 as well. Okay, and so my final result would be that this integral here is equal to e to the sine x divided by 2 plus e to the cosine x divided by 2. And then, of course, don't forget to add the constant at the end. And so that's kind of a tricky way to get the integral here. So what I mean is it's a tricky way to get the result of this integral. Now, by the way, you could combine these two fractions and make it one fraction, where you just had, since they have the same denominator, you could just make it one fraction like this. Let's see. Just add them together, and then you would have e to the x sine x plus e to the x cosine x all over 2 plus c. And so that's how the foldback rule would work on certain integrals. Now the other trick I wanted to show you was if you integrate by parts, and if you continue to get integrals and derivatives, then there's a method called tabular integration. So when you have multiple parts integration, then you can use a method called tabular integration. And let me just show you what you do. So here's how it works. So let's say you have to integrate the product of x squared e to the x. Okay, so what I'm going to do is I'm going to let f of x equal x squared, and I'm going to let g of x equal e to the x. Now in this first column, I'm going to enter f of x, and then below it I'm going to enter the first derivative of f of x, which would be 2x. Then I'm going to enter the third derivative f of x, which is 2. Then I'm going to enter the final derivative here, because you get 0, and any derivatives after that would be 0. Okay, now as far as g of x, now g of x, that should be a lowercase g. But anyway, as far as g of x, we'll copy e to the x here, but we're going to ignore this when we do our calculation. But we're going to do e to the x, and then we're going to integrate. So if we're going to integrate, we'll get e to the x, and every time we integrate, we're going to get e to the x. But now here's the thing though. In this first row, we're going to copy down the g function, and then when we start integrating, we're going to alternate signs. So the first integral is going to be positive, the second integral is going to be negative, and the third integral is going to be positive again. and so you just alternate signs. Now, to get your result, you simply see the arrows. The result, you would say x squared times e to the x, then plus 2x times minus e to the x, then plus 2 times e to the x. And so let's see what that would give me. X squared times e to the x would give me this term. 2x times minus e to the x would give me this term. And then 2 times e to the x would give me that term. And since 0 times anything else is going to be 0, then we wouldn't get any terms beyond that. And so the last thing we add is to add our constants. Okay, so that's the result right there. Now this is the same result you would have gotten had you integrated this using parts the way I showed you earlier, but here you don't have to go through and evaluate all those integrals. Okay, let me show you an example of this. Okay, so I wrote this table just a little bit different, but it's basically the same thing. So here I've got x cubed cosine x, so I'm going to let f of x be x cubed, and I'm going to let g of x be cosine x. And the only difference here is I'm going to put the signs here. Now remember, this doesn't really matter right here because we're not going to focus on this guy. But we will start here with cosine of x. Then you're going to integrate I'm sorry, let me go over here. Let me do it over here. So here you're going to have x cubed. Then you take the derivative of that, you get 3x squared. Then you take the derivative of that, you get 6x. Take the derivative of that, you get 6. And then, of course, the derivative of that is 0. Then over here, you're going to integrate cosine x and get sine x. Then when you integrate sine x, you're going to get minus cosine x. Well, then when you integrate minus cosine x, you're going to get minus sine x. And then when you integrate minus sine x, you're going to get plus cosine x. Now, remember I told you the signs change? So really, for this term, I'm going to get plus sine x. For this term, I'm going to get minus a minus cosine x, so I'm actually going to get plus cosine x. For this term, I'm going to get plus times minus, so I'm going to get minus sine x. And here I'm going to get minus cosine x. So let me show you how it works. So now, remember, we stagger this, so we take x cubed times the sine x, and so that'll give me the first term. And then we take the 3x squared times minus negative cosine x, so that would be plus 3x squared times cosine x. And then we're going to take 6x times plus times a minus, so it's going to be 6x times minus sine x, so that's going to give me minus 6x times sine x. And then we take the 6 and we multiply it by minus cosine x, and so that's going to give us minus 6 cosine x. And then the 0, since all the terms after that would be 0, we're done except for the constant. And so that's how you evaluate integrals by parts, by using tabular integration. Okay, in the next video, I'm going to show you how to use something that's called integration by parts decomposition. So that's where you integrate rational functions by decomposing the rational function into its parts.